Hello, everybody. Welcome back. And let's get started with our topic tonight. We have this, I believe, lecture 17, which is the last part of this module. And next day we'll start on module 8, I believe. Let's see. Module 7. Yeah, we'll start on module 7. This is module 6, the last one of the module 6, and we'll start on module 7 from next class. Okay, so on this topic of this logic design component, I hope you guys reviewed that. Let me know if you have any question on this part. I don't see any question on the discussion as well. Okay. Let me see. James Chian, can you tell us what is a line decoder?
I'm not really sure.
Okay. How about Kevin Nigwen? Kevin Nigwen? Kevin Dwee Nigwen? Oh, he's not here. Okay. How about Fong Nigwen?
Yes, hi.
Can you tell us what is a line decoder?
Line decoder is a type of, it's a sort of like a logical circuit, I guess, that it uses a sort of like format with different minterms and different terms that you plug in. I don't know how to like specifically describe it for you, but that's as much as I can say.
Okay, yeah, you're kind of there. Yeah, definitely it's a logic circuit and
Yeah, I just don't know how to put it into words.
yeah,
Sorry.
it's okay. It generates the mean term. Formal definition wise, as a line decoder is a decoder circuit which has exactly 2 to the power n number of output representing each of the mean term of the n input combination. So that's a line decoder. So whenever we talk about a line decoder or in general decoder in our context, it is a line decoder always. And it has 2 to the power n number of output always. All right. Then let me see. Is there Kyle today present with us? Kylie? No, not Kylie. How about Dominic? No, Dominic is not present either. Okay. All right. Then let's do a problem tonight. And let me share my screen with you. Okay. Oh, where is that? Just hold on. Let me set this up. Okay. Hey, sorry for that. I have some issues here at my computer. Let's see. List. Okay, so we all know this is a 4 by 1 bit multiplexer picture. Let's do this problem first. Like this is a 1 bit 4 by 1 multiplexer, right? Now, if we want to have a 2 bit 4 by 1 multiplexer, how many fundamental logic gates would be needed? Like fundamental logic gates in the sense it's a 1 bit inverter or 2 input NAND or 2 input NOR gate. How many of them is needed? That's the problem. So let me, down the problem as well. 2 bit 4 by 1 mux. Okay. So this problem, like if we want to do it for the 1 bit multiplex, I just want to count the gate count over here, fundamental gate count. What shall we get there? We will have, we can see definitely there are inverters. There are inverters, right? And each of the AND gate that we know, like each of the AND, 2 input AND, it is equivalent to 2 input NAND followed by an inverter, right? This is an AND gate. And then we have one big OR gate, 4 input OR gate, right? It is kind of an that we can actually do like this. This is almost like, let's derive A or B or C or D. Now, if we want to do it like A or B or C or D, NOR and inverter. So what we need to do is actually we can do a better thing here. Just hold on. Let's put De Morgan in place. Okay, and this is nothing but we have inverter basic gates, and then we have like NAND with CNAND DNAND. So it is basically converting this guy into some sort of like big NAND with inverter in it. Okay. And 4 input NAND, we can possibly do like this. This one is Yeah, something like that. Okay. So yeah, though we need to check that. Okay, I'll check it later and we'll let you confirm me about this one, logical equivalency of this. But let's assume this is true for this case. And in that sense, what we have, we can immediately count like two inverter for here, like two inverter. And then each of these AND gate has one inverter and one NAND, one inverter, one NAND. So that means we have how many NAND gate? One, two, and we get 1, 2, 3, 4, 5, 6, 7, 8. So 8 AND gate equal to 8 multiplied by, or it's nothing multiplication there. It's 8 NAND plus 8 inverter. And then we have this big 4 input OR one that would contribute to 4 inverter and 3 NAND. And we are all talking about like 2 input, 1 bit, 2 input NAND in this case. So our final count would become like we have 2 plus 8, 10 plus 4, 14 inverter. And then we have 8 plus 3, 11 NAND. Okay. And you can derive this A or B or C as like cascade of OR gate. A, B, C, D. And each OR gate is nothing but a NOR gate followed by an inverter. So you can calculate with this equivalent circuit too. This is also correct if you want to do that. Question so far? Okay, now the question becomes, how do we make this simple thing to extend for the 2-bit 4x1 multiplexer? Okay, so let's try that. Let me put that. So this is your 1-bit 1-bit 4x1 multiplexer. Now how we change it to 2-bit? First of all, conceptually, this means these guy, each of them are 2-bit, right? And these 2-bit means this I0, I1, I2 2-bit means really there are like two individual logic line like I0, 0 and I0, 1. And similarly for the I1, also it has I1, 0, I1, 1, and so on and so forth for I2, I3, rest of them. And they are basically going to the AND. Now, what is this AND? Like, how can we have a two input handle there? So this is really what boils down to. Let's talk about that M0, connection M0. And here we have 2-bit I0, let's say, this one. So this really means we have like two AND gate. M0, another AND gate is driven by that same M0, and other is driven by each individual bit of I0. Okay, so this is also like two input in that sense. So really internally you have like, for a 2-bit, you have like two of them, two of the AND here, right? Two of the AND. And that means for each of them, this is 2 and there is 2 and there is 2 and. So really, with respect to our previous calculation, our number of AND gate will get changed, right? In that state, this stage. So number of AND gate of this stage will get changed. There will be no change with respect to this guy. This guy won't have a change. This decoder. Decoder will be same. No change. Like decoder is a decoder, is just producing things there. And there will be change for this guy, right? This 4 input and 4 input OR. Now this is again, like you can imagine there is 2 4 input OR. For each of these individual bits coming out of these circuits results. So essentially what we need to do, we need to calculate this OR part twice. So in a sense, that means let's count for the inverter, for the decoder part, we have like this thing, 2 inverter and 4 AND, that means 4 NAND plus 4 inverter. Now the enabling circuit part, we have we have 4 2 input. There is a 4 AND individual AND, but each of them is basically composed of 2 individual AND gates. So we have total 8 AND. That means 8 NAND plus 8 inverter. And about this OR, now let's try in other way, right? Or this is equivalent to like this. Let's do that calculation. Okay, this is a 4 input OR. So each of them individually is a NOR with the inverter. So that means for this combination circuit, combining part, we have how many? Like 2 4 input OR, which is like so each of the 4 input OR will have 4 NOR, 4 inverter. So that means together 8 NOR plus 8 inverter. So that means my total is going to be 2 inverter, 4 inverter, 6 plus 8, 14 plus 8, 24. 24 inverter. Now, and we have NAND, 4 NAND, 8 NAND, 12. Okay, 12 NAND. And NOR we have 8. So 8 NOR. So these are the number of fundamental gates we need to build up a 2-bit 4x1 multiplexer. Question? Okay, now let's extend this problem to a 4-bit 8x1 multiplexer. Okay, so let's see, 4-bit So this is our problem now. Now we need to compute how many fundamental logic gates, which are like these: 1-bit inverter, 2-input NOR, 2-input NAND, and 1-bit inverter. These are needed for a build 4-bit 8x1 multiplexer. Let's do this in group, and then we'll discuss on the result. There's some content. Okay. Let's take about 15 minutes for this problem to solve in group. Then we'll rejoin and discuss this problem. Okay, let's see what you came up with that counting. How about study group 4? Fong Neguen, Rahul, and Yang Zhang. Anyone of you wants to share the solution or what you did describe?
We just attempted to try and figure out how it would look, but I
Mhm.
don't think we really got anywhere with it.
Okay, but can you explain your approach?
Well, like I said, I was just trying to put the circuit together. But I don't
Hmm.
really I didn't really have much, so
Okay,
I don't I don't think I can share it. Sorry.
okay. Uh, yeah, how about others in your group? Did you guys discuss this problem or just worked yourself?
This time I was not able to finish all the lectures, so I just went back to the lectures and tried to get
Oh,
that code because I was not able to understand I mean, the 8x MUX. I was not able to understand what that meant and how to interpret that. So I was just going through the lectures and notes again and again.
okay, all right. Okay, let's turn to then group number 9. Uh, Chen Hui Su and Quinlan Nguyen. You guys have done this problem?
No, you didn't quite get it, but we were thinking that since it's a 4x1, and there's like 4 AND gates in the enabling circuit, we were thinking that there's gonna be at least 8 NAND gates and 8 inverters.
Okay.
And like from the previous example,
Mhm.
since it was a 2-bit system, we were guessing that at least 32 NANDs and 8 inverters would be for the enabling circuit,
Mhm.
because we had to multiply it by 2, but we weren't able to find out the exact number of gates, fundamental logic gates we needed.
Okay. Okay, that's okay. Then why don't I just show you? First of all, you guys do not need to construct the full circuit to do that. It's more like a conceptual perspective. Let me try to explain what approach you need to take for this problem. Okay, let me share. So you see that for a 8 by 1 multiplexer, 8 by 1 multiplexer, what you need to have definitely is a 3 by 8 line decoder. Remember in the previous example, we have 4 to 1 multiplexer. So that's where we needed actually 2 to 4 line decoder. Now, since we have 8 by 1 multiplexer, we need to have a 3 by 8 line decoder. So in general principle, if we are given with a problem like n by 1 marks, we need definitely a log base 2 of n ceiling that line decoder. That by n line decoder. Now for this line decoder part, you see like if there is a 2 by 1 line decoder, for example, what we have? We have like one inverter and then we just have one inverter, nothing else basically. Your output is like, well, what I'm saying. It's not 2 by 1, it's 1 by 1 to 2 line decoder. 1 to 2 line decoder. Now, if it is a 2 by 4 line decoder, then what we have? We have like inverter, 2 inverter, just like previous example, and 4 AND gate, right? Similarly, if you have 3 by 8 line decoder, I'm not showing the exact connection, just component wise, definitely you need to have 3 inverter to make that inversion terms. And how many AND gates would be there? Definitely 8. 8 AND gates, 1, 2, 3 till 8. 1, 2, 3, 4. So you see the pattern here is if we are talking about an something by n line decoder, that means it has n number of AND gate, no matter what circuit you come up. It has at the output stage, it has 8 line decoder, right? And then you need to think like how you are going to combine them, right? Each of them, see the 3 lines. There are 3, like this is 3 terms, A, B, C. So this is A bar, B bar, C bar. So each of them are going to connect it to be 3 of this term to make the mean term, isn't it? Different combination, A bar, B bar, C bar, other is maybe A, B, C, A, B bar, C bar, something like that. But at the end of the day, these AND gates are all 3 input AND gate. Means it is equivalent to 2 input AND gate, isn't it? So that means you can generalize this whole concept towards the n bit line decoder. There is a n AND gate and these many -1 number of 2 input AND gate there. So what I'm saying is that there would be for a n bit, let me generalize the term a little more. If you are talking about m by n line decoder, we'll always have like m number of inverter and m multiplied by n number of AND gate. M minus 1, sorry, M minus 1. M minus 1 multiplied by n number of AND gate. And then AND gate is broken up into 1 inverter and 1 NAND gate for fundamental gates. But this is the whole generic term, like calculation idea for the decoder part, right? Any questions so far? Okay. So for this specific example, let's now count down the components for 3 by 8 line decoder first. So it has how many inverter then? It will have 3 inverter and 3 multiplied by 4 equal to 12 AND gate, which will give me 12 NAND plus 12 inverter. Okay, so inverter 3, 12 NAND, 12 inverter total. Now the other part. Other part, we have what? If we recall, let's look at once more the 4 by 1 multiplexer. So this enable circuit stage will have that many AND gate as number of input, right? So here we are talking about 8x1 multiplexer. That means definitely that stage, that enabling circuit stage. Now let's talk about that one, enabling circuit stage. That logic stage will have definitely, if it is like, and like in general, if it is an n/1 mux, we have that enabler part n number of, right? 1, 2, 3, that stage till n. So in this problem, we have 8x1 multiplexer. So definitely we have 8, and now it question becomes that how many bits? Like we are talking about 4 bit here. That means each of them, each of these guy is basically 4 individual input to accommodate each bit. So these 4 bit, so it expanded to this 4 individual AND gate, 1 input, 2 bit AND gate. So that becomes essentially, we have this number of bit with that number of AND gate. So we have total 32 AND gate at the enabling circuit stage, which means it is 32 NAND and 32 inverter at that point. Okay, so let's bring out the other calculation from here. So we have 3 inverter, 12 NAND, 12 inverter. Okay, so for the decoder part, let's note it down. For the decoder, we have 3 inverter, 12 NAND, 12 inverter. Okay. Now for the enable and circuit stage, we just calculated 32 NAND, 32 inverter. Okay, now so far any question for this till this calculation?
Professor, I have a question.
Yes.
Oh, for the last part, the 12 non-12 invert, where the 4 come from? I was lost on that part. Like 3 times 4, where the 4 come from?
Oh, that comes from this 4 bit.
Oh, okay.
Remember, like our problem said how many for the 4 bit, 8
Oh,
bit.
got it. And
That
other
means
question.
we are talking about 4 individual bits. So that means each of this AND will actually have a 1 bit, like in this case it was having a 2 individual AND there to cater that 2 bit. Now if it is extended to the 4 bit, that means this will be like 4 AND sitting represented by each of these part.
Okay, got it. And I have other question. How do I know this is a 3 to A line decoder from the question? I was lost on the really first beginning.
Come again, sorry.
How do I know from this question this use 3 to A line decoder? I was lost on that part.
Oh, okay. So this was like, if it is an n/1 multiplexer, you need a log to n by n line decoder.
Oh, okay.
Yeah, for example, like it was like 4/1 multiplexer, right? So log base 2 of 4 is 2 and 4. So 2 to 4 line decoder is needed here. Similarly, for 8 bit, we need to have like 3/8 line decoder.
3. Oh, okay.
So 8/1. So you take log base 2, which is 3, right? 2 to the power 3 is 8.
Yes.
Right? So 3/8 line decoder is needed.
Okay, got it. Thank you very much.
Okay. All right. Now let's complete our calculation. Now the next stage is that combining circuit, right? Combining circuit. Which is nothing but a big OR, giant OR, right at this point somewhere, which combining these 8 individual lines, each of them 4-bit. Each of them 4-bit, right? This is 4-bit multiplexer, 4-bit 8x1 multiplexer. So in this case, what you have really is this one. You can imagine you have like 4 of them, individual bits. So this one is nothing but combination of 4 individual 4-bit 4-input OR, and each of them is basically a 3 combination of 2-bit 3 OR. So that means essentially we are talking about how much? 3, 3, 3, 3. Okay, 4-bit. Okay, so we have 8. Oh, sorry, not 4-bit. My bad. That's what I was thinking. So we are talking about 8 of them, right? Because this is like 8-bit, 8 lines. 8 lines. This is 8x1 multiplexer. So these are 8 lines, individual lines coming in. So we are talking about 8. Each of them is 8-bit each, 8 input, 1 output, and we have 4 of them. Eight of them and another 8 of them. So that takes care of your 4-bit and 8 inputs. So this is essentially what we have. That means we have 7 1-bit 2-input OR gate, isn't it? So why? Because if you see, if it is a 4-input OR gate, 4-input OR gate, it's basically a cascading configuration of 3 input, 3 OR with 2 input, right? So similarly, if you want to extend it for the 5 input, 6 input, 7 input, etc., you just have to have one less number of OR to combine with. So that way we can conclude that 8-input OR gate, 1-bit 8-input OR gate is equivalent to 7 2-input OR gate, 1-bit 7 2-input OR gate. So that means we have essentially 7 this thing by 4 of them. So ultimately it becomes like 4 multiplied by 7 1-bit 2-input OR, which is basically we are talking about 28 NOR and 28 inverter. Now we combine them. Now we combine all this component. We have 3 inverter, 12 inverter, 32 inverter, 28 inverter. If we add them up, it comes about 75. 15, 47 plus 28, 47 plus 20 is 67 plus 8, 75. Yeah. So total we have then 75 inverter, and we have 12 NAND, 32 NAND. 12 plus 32 is 44, and NOR we have 28. Okay, question?
Professor.
Yes.
Can you explain one more time for the one bit two input for that part?
Okay, 1 bit 2 input is like our general, like if we are talking about this one, right? Just 1 bit input A, 1 bit input B, and Y is output.
Okay. Okay.
This is 1 bit 2 input OR. That is that, like, which is which is kind of a very low level gate, right? Another thing can be like this. This 4, like 2 input. This is like 4 bit 2 input OR, which essentially means this guy, if you want to construct this one, let me take another page actually to explain this one. So we're talking about like 4 bit 2 input OR. This is basically, we can build up like this with a 4 2 input OR, 4 1 bit 2 input OR. We can build the same thing here. So if we just, let's say ABY as a bit notation, then we can think this is like an bit 0 OR, this is bit 1 OR, then this is doing the bit 2 OR, and this is bit 3 OR. And this is your output 0, output 1, output 2, and output 3. So essentially what it means, like when we draw a schematic, something like this, we really internally, we mean fundamentally it has this thing. Not really fundamentally, right? You know that this thing is now, you need to implement like this. NOR, fundamental get, and this. So fundamentally it has this circuit inside. So this is what we mean. Like when we say about 4 bit 2 input OR, we really mean inside there is a fundamentally there are four 1 bit 2 input NOR and 4 inverter. Make sense? Yeah.
Yes, got it. Solid. Thank you.
Okay. All right. Anything else? Okay, if we don't have any other question, then we can stop for tonight and see you on Thursday.